Welcome to Adventures in Mathematics. I am your instructor, Alan Carlisle. Today we're going to look at a hypothetical experimental situation. Suppose that you throw a single die 8 times in a row. You would like to know the probability that you will throw exactly 2 sixes. One way or outcome that will produce this event is illustrated below with the probability shown for each throw of the die. Alright, so we have trial number 1, 2, 3, and so forth up to trial 8. On the first trial, you throw a 5, which even though throwing a 5 is a probability of 1/6, it is not throwing a 6, so it's failure. In this series of trials, which by the way is called Bernoulli trials, you'll either have failure or success. So the event of not throwing a 6, failure, is or has a probability of 5/6. So if you throw a 5 on the first row, that's 5/6. Failure to throw a 6 on the second row is also 5/6. If you throw a 6 on the third row, that's 1/6, and so on. So in other words, here's a situation where you throw a 6 on the third toss and on the 7th toss, and failures in all other tosses. Because these events are independent, you can multiply the separate probabilities together and end up getting 5/6 to the 6th power times 1/6 squared for the probability of the event occurring in just this manner. Okay, now the arrangement of successes and failures is the next aspect of our final probability that we're looking for. If you consider this event of throwing 2 sixes exactly in 8 throws of a die, we just calculated one possible arrangement of failures and successes. So what we have to do now to complete this is to determine the total number of arrangements. For example, what we just calculated was the probability of throwing the 2 sixes on the third roll and on the 7th roll. All of the rolls gave us failures. So what we're looking for is a way of calculating the total number of arrangements possible of 8 items. All right, to make the analysis understandable, we're going to set up a correspondence between a set of objects. I chose the letters A through H, 8 of them, and the arrangement of failures and successes, what we just looked at. Notice that C corresponds to S and G corresponds to S. So this particular arrangement of failures and successes would also correspond to the combination CG. Another example of this simple concept is shown here. Let's suppose that the success was on the 2nd throw of the die and on the 5th throw of the die. This arrangement of failures and successes would correspond to the combination BE. How many combinations are possible? Well, every math student should know the answer to this is shown as the number of combinations of 8 objects taken 2 at a time, 8 factorial divided by 2 factorial times 6 factorial, which turns out to be 28. So there are 28 possible arrangements of 6 failures and 2 successes. In general, the formula for the number of combinations of n objects taken r at a time is one that's shown here that most of you should already be familiar with. In general, if the probability of an event is given by the variable p, and we have a series of trials we call Bernoulli trials, where either the event occurs or it doesn't occur, and n represents the number of trials, then the probability of k events occurring in n number of trials is given by this probability density function, the number of combinations of n objects taken k at a time, which we just looked at, times the probability of success to the k power, times the probability of failure, that's 1 minus p, to the n minus k power, where p is the probability of success, 1 minus p is the probability of failure. This is known as the binomial distribution. Okay, the probability of success given by the variable p can also be expressed as lambda over n, where lambda represents the average or the expected value, the number of successes of the event within n number of trials. Now we're going to look at what happens to the binomial formula that we just solved, the binomial distribution formula, as n increases without bound. But before we do that, let's first justify that p equals lambda over n. In our die throwing experiment, we could say that in 6 trials we would expect 1 occurrence of throwing a 6. This translates into lambda over n equals 1 over 6. We can extrapolate this result to other Bernoulli trials. But first, the answer to our original problem now becomes the probability of throwing 2 6s in 8 casts of a single die is given by the number of combinations of 8 objects taken 2 at a time, times 1 6 squared, times 5 6 to the 6th power, which is approximately equal to this value here, 28 times 0.0093, which equals 0.26. Now, let us consider what happens as we increase the number of trials without limit, without bound. In other words, as n approaches infinity. The number of trials in a Bernoulli trial, n, will be within a certain constrained time limit. So if each trial is separated by a subinterval of time we will call later delta t, then conceptually delta t gets smaller, approaches 0, in other words, as n increases without bound. Now, to understand what happens to the binomial formula that we see here, binomial distribution formula, as n increases without bound, we substitute into the formula for p lambda over n, and we get this. Okay, the number of combinations of n objects taking k at a time, shown here. P p to the k power, shown here. 1 minus p to the n minus k power, shown here. Actually, we separate using the fact that 1 minus p to the n minus k power can be separated into two factors this way. And this can be rewritten as the limit as n approaches infinity of n factorial over k factorial times n minus k factorial times lambda over n to the k power times the product of these two factors here. Everything is in terms of n, k, and lambda. Now what I'm going to do is, after I rewrite this expression as lambda to the k over n to the k, I'm going to switch out n to the k, which would normally go here, with k factorial, which normally goes over here. Just switch the two. The reason for that will become apparent in a moment. Now it's pretty easily shown that this particular factor here that I'm circling approaches 1 as n gets larger. This fraction gets closer to 0, which means this number gets closer to 1, and of course 1 to any power equals 1. So we've just shown that as n increases, this factor goes to 1. And now let's consider what happens to this factor when I'm circling. If you will notice, we have n factorial over n minus k factorial, which can be simplified as simply a series of factors in the numerator, which I have delineated here as n times n minus 1 times n minus 2, etc., with k number of factors. We therefore have n times n minus 1 times n minus 2, etc. in the numerator, k number of factors, all over n to the k power, taking the limit as n increases without bound, using the fact that the factors in the numerator can multiply together to give us a polynomial of degree k, taking the limit as n approaches infinity, and multiplying both numerator and denominator by 1 over n to the k, we now get this expression which approaches 1 as n approaches infinity. Every factor after the 1 goes closer to 0, and the entire expression approaches 1 over 1, which of course is 1. Therefore we can conclude that the limit as n approaches infinity of our entire expression can be simplified to this limit here, lambda to the k power over k factorial times 1 minus lambda over n to the nth power, which delightfully becomes the limit as n approaches infinity of lambda to the k power over k factorial times 1 minus lambda to the n, lambda over n to the n power. And everyone should recognize that as n approaches infinity, this particular expression approaches Euler's number to the negative lambda power. Remember, Euler's number is 2.71828 approximately. And now we are done. This is the continuous analog of the binomial expansion, or the binomial distribution, and it's called the Poisson distribution with mean of lambda, the mean or average value lambda. Let's take an example from real life to see how we might use this particular probability density function. Suppose it's known on the average there are 2 car accidents at a certain intersection every month. Assuming that the number of accidents at this intersection has a Poisson distribution, and many real-life situations do, what is the probability that there will be 4 accidents there this month? In other words, lambda is 2, and we want to find the probability that n equals 4. Plugging that into our Poisson distribution formula, we get 2 to the 4th over 4 factorial times e to the negative 2, which calculates to approximately 9%. And it is a fact that the Poisson probability distribution fits many real-world situations very nicely. Here is a graphical representation of the Poisson distribution for 3 different parameters of lambda. For lambda equals 1, we have this, and keeping in mind the fact that the Poisson distribution is for discrete random variables, k. Even though lambda itself doesn't have to be an integer, positive integer, k itself is. This is a discrete probability density function. But anyways, as lambda gets larger, for example, lambda equals 4, gives us something that begins to take a familiar shape, and as lambda gets even bigger, equaling 10, this begins to look more and more like a familiar bell curve. Now let's suppose we perform a series of Bernoulli trials where an event will occur with probability p or not occur with probability 1 minus p. We seek the probability of 1 success, casting 6 with a die, for example, on the 11th throw. Since each throw is an independent event, we multiply the probabilities of casting anything but a 6 on 10 throws of the die, together with the probability of casting a 6 on the 11th throw to get 5 6 to the 10th, multiply times the probability of throwing a 6, 5 6 to the 10th times 1 6, approximately 0.0269. In general, in a series of trials of an event's success or failure, with the probability of success equal to p, the probability of the event occurring on the nth trial, assuming it does not occur on any successive trial, is given by this expression, p times 1 minus p to the n minus 1 power. This distribution is called the geometric distribution, and of course it is a special case of the binomial distribution that we've just analyzed. Now we're going to consider the same series of trials, throwing a die in succession over a specified period of time. Alright, let's suppose that you've cast a die every delta t seconds, or minutes, or some unit of time. Of course, delta t represents some sub-interval of time. Now we're going to seek the probability that no 6 is cast in the time interval from t0 to time t. In other words, from here to here. Now, n, little n, represents 6 in this particular case because we're still using the die, and the event of success is throwing a 6, and so we would expect on the average every 6th cast of the die to give us success. And in this particular arrangement, we're looking at 15 time intervals. Okay. Capital N represents the number of trials from time t to t naught, which in this case is 15. The probability of success is 1/6. The mean number of time intervals, delta t, until success is 6. Right. And the mean time until success is given by u. Let's get these straight, because these three very simple equations are going to become very important here as we let delta t approach 0 and capital N get larger without bound within a specified time interval from time t naught to time t. Notice that the probability of success is 1 over n, little n that is. Little n times delta t is u. In other words, 6 delta t units gives us the mean time until success. The mean number of time intervals until success given here. And of course we have capital N, the number of delta t subunits within the entire interval. If we multiply the two together, we get t, the length, total length of our time interval. Clearly from the geometric distribution, the probability of not casting a 6 in 15 throws of the die is given by P of n equals 15, is the probability of failure to the 15th power, which is approximately 6.5%. And in general, if there's a series of trials or an event can occur with probability P, and we perform n number of trials within a specified interval of time, of course, then the probability the event will not occur within the n trials is given by 1 minus p to the nth power, again from the geometric distribution. Rewriting p as 1 over n, and n as capital N, the number of delta t subunits within the entire interval, as delta t times n, making these substitutions into this expression that represents the probability of all failures, we get this. Now, we take the limit as delta t approaches 0, and, well, of course, this limit does exist and can be easily shown to equal e to the negative 1 over u times t, so that the probability of no success within the time interval is equal to e to the negative 1 over u times t. T is the length of the interval. U is the mean time until success. Now, let us assume that only a single success is allowable within the interval. We can choose an interval small enough so that more than one success will be virtually impossible. Or we can simply make the rule that once a person throws a 6, then he stops. Okay? Now, from probability theory, we know that to find the probability that something does not happen, we can subtract it from 1 to calculate the probability that it does happen. And in this case, since the probability of not throwing a 6, or a probability of success within the time interval, is given by this expression, and when we subtract it from 1, we get the opposite of that event. Well, what is the opposite of not having a success within the time interval? Well, it's this: the probability of a random variable x, the time at which success occurs, in other words, is less than the given time interval t. Now think about this for a second. This represents, that I'm underlining here, the probability that there is one success within the time interval. This is very interesting. Okay, what we've just derived is actually a cumulative distribution function for the random variable t, so that the probability that some random variable x is less than or equal to t, in other words, that success occurs somewhere within the interval, is given by this expression here. Now, to find the corresponding probability density function, we simply take the derivative of this distribution function. You probability students out there should be aware of this fact. Once you take the derivative, you get the probability density function, which is the exponential distribution with the parameter 1 over u, where u represents the mean time between successes. The expected value of t is found by evaluating. Okay, the integral from 0 to infinity of the random variable t times the probability density function that we just derived, dt. This evaluates to u, in other words, the mean time between successes. Putting all this together, if an average number of events k occur within some time interval t, then the probability of n events occurring in the same time interval is described in the Poisson distribution, recalling that to be given here, where lambda is the mean number of events in the specified time interval, and the mean time between events has the exponential distribution, which we just found, where u is the mean time between events. It's very important that you note that u and lambda are reciprocals of each other, which makes sense if you take, for example, that a store gets an average of 4 customers every hour. This is the same as saying that the mean time between customers is 1/4 hours. What we've developed here is a mathematical analysis of what is called the Poisson process. Queuing theory is a mathematical study of waiting lines, or queues, using the results that we have determined here and derived. A major point that we need to bring out is that the Poisson process involves memoryless probability functions. In other words, probabilities of events happening within a time period are independent. If a success happens, it happens independently of what might have occurred before. Or if a success does not happen, that's independent of what happened before. Which means that we can start at the actual occurrence of a successful event, at that point being t naught, and looking at the next time interval from t naught to t. The probability of t is of exponential of the exponential distribution. Okay, let's work an example to get a good feel for what's happening and how to use these formulas in a Poisson process. We need to know how to modify these functions in order to accommodate the actual event. For example, suppose we would like to calculate the probability of catching 10 fish exactly in a 12-hour period of fishing if the mean time between catching a fish is 40 minutes. Of course, the parameter 1 over u translates into 1/40th. This is equivalent to 1/40th times 720 minutes, since our units is going to be in minutes, and 720 minutes in a 12-hour day. This translates into an average of 18 fish per 12-hour period. That gives us our lambda to be 18 fish. And in general, the mean time between events u is within some specified period of time t would be represented by 1 over u times t. And in general then, if the mean time between events is given by u, then the mean number of events within time t would then be given by t divided by u, and the probability of k events in this period of time would then become, using the Poisson distribution formula, given by what I'm circling here. Therefore, the probability of catching 10 fish calculates to 18 to the 10th power over 10 factorial times e to the negative 18, which is approximately 1.5%. Now suppose you wanted to know the probability of catching 10 or less fish. This would require that we add up all the probabilities from catching 0 fish to 10 fish. You can do that since these events are mutually exclusive. And therefore, we would have the probability of catching 10 or less fish is equal to this sum, letting n equal 0 to n equal 10 of our Poisson distribution. This works out to be approximately 3%. I've enjoyed this adventure in mathematics with the Poisson process and the intriguing and remarkable functions that we were able to derive and use. And believe me, there are many real-world applications of what we've just studied. So have a good day, and until next time, I'm your instructor, Alan Carlisle. This is Adventures in Mathematics.